In this set of notes, we're going to look at maximum likelihood estimation. So to start out here, I have just a little bit of a historic note about likelihood theory. And so it ends up that likelihood has a long history in statistics. It was largely due to work from the 1920s, and really a lot of the inferential procedures that we do are built on this idea of likelihood theory. So let's just start out by defining our likelihood function. So if we let x1 through xn be random variables, the likelihood function is defined as follows. And so we have here that the likelihood of theta given x1 through xn, and the way that I've got it written here, theta is written as a single parameter, but really theta can be a vector of parameters, so it doesn't just have to be, a single parameter. And we use the symbol theta here to just be a generic placeholder for whatever parameters that we're interested in. So I don't want to look like that this only applies to distributions, that we typically use theta as the notation. This could apply to any of the distributions that we've looked at. So for example, if we were working at a normal distribution, theta could be used to represent the vector of parameters where the two parameters are mu and sigma. So we say that the likelihood of the parameter given the random variables, or in this case, since they're given, we're actually going to say the observed data here in a moment, is equal to, and here we have either the PDF or the PMF of the random variables, depending on if the random variable is discrete or continuous. So in other words, what we're saying is if we let f of x given theta denote the PDF of the sample x1 through xn, then given the sample x is observed, and so here notice I'm using a bold x, so what I'm doing that is kind of a placeholder and saying that bold x is really, it's equal to x1 through xn. Notice there's no a subscript on it, so that's just a shorthand to represent x1 through xn, is observed, the likelihood function of theta is defined to be the following. So on the surface of things, this seems pretty uninteresting. The likelihood is just the same thing as the PDF. It just seems like it's a change in notation. But really what's going on here is it's a change in what we're given and what we're looking at the likelihood or the probability of. So it's crucial to keep in mind that f of x given theta, that's a function of x, and here again, that really should be bolded, with theta known. So for example, if we were talking about the normal distribution, we could say, what is the probability that we observe, x to be equal to 10, given that mu is equal to 11 and sigma is equal to 2, or I should say x like less than 10, not equal to 10, since it's continuous. While on the other hand, the likelihood of theta given x, that's going to be a function of theta with x known. So what this means is that while f of x given theta measures how probable various values of x are for a given value of theta, the likelihood of theta given x measures the likelihood of a set of parameter values given the observed outcomes. And so if you think of what you do in practice, it makes sense why the likelihood is so important. In practice, what do? We go out and we collect observations, and our question is usually something about parameters. So if I go out and I collect blood pressure for 100 subjects, the real question that I want to know is, what is the population blood pressure? In other words, what would mu be? And so based on what I observe in that sample, hopefully I can figure out what reasonable values of that parameter are, and that's essentially what the likelihood allows us to do. It allows us to look at how likely values of the parameter are given what we observed in our sample. And so what we can do is we can compare the likelihood for two different values of theta, conditional on what we observed in the sample, and figure out which of those two values of theta are more plausible. So in light of the data that we've gathered, that the true value of theta is theta 1 more so than it is theta 2. And so that's what the likelihood gives us to do. Now, one thing that I do want to note here is, I've got the likelihood written fairly generically here. We've got it written in terms of a sample of x1 through xn, but there's nothing that says we couldn't just look at the likelihood for a single observation, and so you are going to look at that in the homework. And so, for example, if we just had one observation, let's say I wanted to write the likelihood for xi, notice that that would just be L of theta given xi, and then, if we were looking at a continuous random variable, that would just be f of xi given theta. So you can write the likelihood just for a single observation, or we can write the likelihood for multiple observations. So of course we need to address the question of how meaningful a given difference is between likelihoods, but certainly it seems reasonable to ask how likely it is that we would have collected data we did for various values of the unknown parameter theta. So perhaps again the most basic question is, which value of theta maximizes the likelihood? And so we saw maximum likelihood before, and so the big idea is you've been given this sample, we have this likelihood, so which value of theta is most likely based on our sample? And that's what maximum likelihood does for you. And so the idea here is that we're going to estimate the parameter by choosing the values of the estimate which maximize the likelihood. So maximizing the likelihood is the same thing as maximizing the probability of obtaining the data we observed. It's often easier to work with the log likelihood function, and so we've seen that before, and that's more just for computational ease. And then, assuming that the log likelihood is differentiable and bounded above in theta, the maximum can be found in differentiating with respect to theta, setting equal to 0 and solving. So in other words, we find this right here, and this is what's known as the score function. So we're going to look at an example of this and all of the different pieces. All right, so we're going to look at a maximum likelihood example using the exponential distribution. So here we're going to let x1 through xn be IID exponential with parameter lambda, where we have the following. And so here we've got x greater than or equal to 0, lambda greater than 0, and we are observing x1 through xn. And we're going to find the maximum likelihood estimator, or MLE, of lambda. So one thing that I do want to point out, all right, so one thing just to kind of remember here, we are working with the exponential. We always want to be careful with any of our distributions that we work with, because as we've seen in the past, there's different ways to parameterize them. So this is the parameterization we're using here, but other parameterizations will look at 1 over lambda and then negative x over lambda. So just always keep that in mind. So once we get the MLE that we find is going to be dependent on the parameterization of the distribution. So if you were to go online and you look up, what is the MLE of the exponential distribution, you may find something that's just slightly different, and it will be because they've used a different parameterization. And it ends up that, there's a one-to-one correspondence between them, but we always want to be careful which distribution it is that we're working with. So for starters here, let's just start out by writing out what our PDF looks like here. And we've already got it here, but let's write it in terms of xi. So here we have f of xi given lambda is equal to lambda e to the negative lambda xi. And so then what this tells us, if we wanted the likelihood of a single xi, we could write that the likelihood of lambda given xi is equal to lambda e to the negative lambda xi. And so what you're going to find in the homework, I'm going to ask you to write out what is the likelihood for a single xi. And then you'll go through and find that maximum likelihood for just that single one, and then you'll do some other stuff with it that I'll talk about here in a minute. But let's continue our example that we have here. Now here, we're actually going to go ahead and write out our likelihood in terms of x1 through xn. So here we've got the likelihood of lambda given x1 through xn, and notice since x1 through xn are IID, we could actually write this as a product of the individual likelihoods. Now, if we didn't have that independence, we couldn't do this. So this is one of the reasons that a lot of times you see that independence assumption is because underlying you've got some kind of likelihood theory in there. We know if we're going to use MLEs, we need that independence. If we don't have that independence, our calculations become more complex. And that's not to say we can't work with data that's not independent, but we just have to make sure we're careful about what assumptions we're making and when we make them. And so this is going to be equal to the product, I equals 1 to n lambda e to the negative lambda xi. Okay. And next, what our goal here is, we've got our likelihood written out, is we need to find values of lambda which maximizes the likelihood. So a lot of times if you're going to find a maximum or a minimum for that matter, we often work with differentiation. And so notice here, since we're wanting to find the values of lambda, we want to differentiate with respect to lambda. And so if we were just going to go through and differentiate the likelihood, I don't really want to differentiate that. That looks kind of nasty. I'd rather differentiate with something that's a little bit easier to work with. And so we notice that the log likelihood would be easier to differentiate. And because of the properties of logs, whatever value of lambda maximizes the likelihood, it's also going to maximize the log likelihood. So we're safe to work with that log likelihood. So let's take the log, and remember when we take the log likelihood, that's usually denoted with a lowercase l instead of the uppercase. So we know that the log likelihood is just going to be equal to the log of the product, I equals 1 to n, lambda e to the negative lambda xi. And then using our properties of logs, remember that what happens is if you have a product on the inside of the log, that becomes a summation. So we end up with the sum I equals 1 to n log lambda minus lambda xi, and those are all inside of the summation. So now let's carry the summation through. Here, notice that the first term doesn't depend on I at all, so this is just going to become n log lambda, and then our second term is going to become lambda. Since lambda doesn't depend on I, the sum I equals 1 to n xi. So notice really what the log does for us is it allows us to look at a derivative that instead of involving a product, it's going to involve sums, and we would much rather take derivatives of sums than products. And so that's really all working with the log likelihood is doing for you. It's really a convenience. So when we take the derivative, it's much easier to work with. So next, we're going to take that derivative. So we have the derivative of the log likelihood of lambda given x, and here for shorthand I'm just going to write lambda with respect to lambda. And so looking at our first term, we end up with n over lambda minus the sum I equals 1 to n xi. And this is what we call the score function. So why would we give this its own special name? The reason for this is, remember that our next step that we're going to do to find the MLE, we're actually going to set this piece equal to 0, and we're going to solve for lambda. So once you get down to this step, you really already have your MLE. The rest of it, again, is just setting equal to 0 and solving. So notice that the score function really defines what the MLE is. So that's why the score function gets its own kind of special name here, is because once we have the score function, we know what we're working with. Right? So let's go ahead and finish. We're going to next set the score function equal to 0 to get the MLE. And remember that once we set it equal to a value, we actually no longer want to write this as lambda. We want to write it as lambda hat. Because once we set it to equal to 0, we recognize that we've set it equal to a value, and now what we're doing is we're looking for our estimate. And then if we solve here, we're going to solve for lambda hat, and we end up with lambda hat is equal to n divided by the sum, I equals 1 to n xi, and notice that this is really equal to 1 over x bar. So for the exponential distribution with this particular parameterization, the MLE is equal to 1 over x bar. Now, if you looked at a different parameterization of the exponential distribution, again, one of the most common ones being that instead of lambda, you would have 1 over lambda or 1 over some other Greek letter they'll typically use, you would actually find in that scenario that lambda hat's equal to x bar. So again, what we end up here for the MLE is going to be dependent on the parameterization that we use, but there's a one-to-one correspondence there. You can move between them. All right, so that's a little bit of a review on the MLE. Now, what I'd like to do is talk some more about this score function. Okay, and it ends up that the score function when we work with generalized linear models is going to be really useful. All right, so given that so much of maximum likelihood estimation revolves around A, working with the log likelihood, and B, taking its derivatives, it's perhaps unsurprising that the derivative of the log likelihood is given its own name, the score. So formally, the score, commonly denoted as U, is defined as the following. And we can see if we look at that example that we had above, that's exactly what we did. Now, one thing to note is that you can define U for a single xi. And so, for example, for an individual xi, we could define it as U of xi of theta, or for notational purposes, we often will drop the x, so you could just have U of I of theta. And so if you were going to calculate this, if we look at that above example that we had up above, so let's kind of go back just a little bit. If we were to find that for an individual xi, notice essentially what we would do is we would take the likelihood for the individual observation, take the log of this, then take the derivative of that log with respect to lambda. And that would give you U for the individual xi. And so a couple things to note here. U is going to be a random variable because it depends on x, and it's also a function of theta, the parameter. These will often be dropped for the sake of convention and notation, and you see that right here. And with IID data, the score of the entire sample is the sum of the scores for the individual observations. So notice if we find I for an individual observation, to find U for the entire sample, we could just take the sum of those. So again, going back to our exponential distribution. Up here, if we did exactly what we just talked about, we started with this likelihood, we took the log, and then we differentiated with respect to lambda. That would give us the score for a single xi. Then, if you take the sum of that from I equals 1 to n, you would end up with this exact same score function. Okay, so thinking about maximum likelihood estimation in terms of the score, we see that the MLE is found by setting the sum of the observed scores equal to 0. And that's exactly what we did for the exponential distribution. So let's talk about the mean of the score function. We now turn our attention to the theoretical properties of the score. It's worth noting that there are some regularity conditions that f of x given theta must meet in order for these theorems to work, but for the purposes of this class, we're going to assume we're working with a distribution for which these hold. And this is the case for the vast majority of common situations, but there are some exceptions. So it ends up that the expected value of u is always going to be equal to 0. And then in terms of the variance of U is also given a special name in statistics. It's called the Fisher's information, or simply the information. And we had mentioned information previously, but we didn't go into depth in 675 when we looked at the Kramer-Rao lower bound. So in this class, we're going to denote the information with a capital V to emphasize this relationship. Again, though, this is just the notation we're using here. Like most things that you've seen, that notation will change slightly from resource to resource. So like the score, the information of a function is a function, of theta, the parameter. Although unlike the score, it's not random, as the random variable x has been integrated out. So let's look at why that is true. So if we wanted to find the variance of U, so let's just review what we know about variance. We know that the variance of U is equal to the expected value of U squared minus the expected value of U, the entire thing squared. But remember that we already said that the mean of the score function is equal to 0, so this is just the expected value of U squared minus 0 squared, which obviously is equal to the expected value of U squared. So that's where this is coming from. So that's just using those properties that you've seen in the past. And it ends up for IID data. Each observation contains the same amount of information, and they add up to the total information in the sample. So again, you could just find the variance of a single, for a single observation, and then look at the sum of those to get the full variance. Now, when you look up information will sometimes be written just in terms of the variance, but if the log likelihood is twice differentiable with respect to the parameter and under certain regularity conditions, you can also write the Fisher's information as the negative expected value of the second derivative of the log likelihood with respect to the parameter. So you'll see both of these often written in text, but as long as you're under those certain regularity conditions, and for this class we're pretty much always going to be, you'll find that these are equivalent statements. All right, so let's continue our example with the exponential distribution and kind of look at examples of each of these pieces. So we're going to start out here with the score function. So we already showed up above that the score function here, and here I'm going to denote it as U of x because I'm going to look at the score function for the entire sample, and we could just shorthand that to be U, is equal to n over lambda minus the sum I equals 1 to n xi. So we claim that the mean of the score function is equal to 0. So let's see if that's actually the case for our example. So we want to find the expected value of U, where here U is equal to n divided by lambda minus the sum I equals 1 to n xi. Well, looking through here, notice the only thing that's random is x. So if we take the expected value of n over lambda, that's just going to be n over lambda. So we have minus the expected value of I equals 1 to n xi. Then we're going to use that linearity of expectation that we've seen before. So we can move the expected value in. And then recall here that xi is distributed exponential, and for that parameterization of the exponential distribution, we have that the expected value of xi is equal to 1 over lambda. Okay, so now, oops, sorry about that. Bring that back. So now our term inside of the summation does not depend on I, so we end up with n divided by lambda minus n divided by lambda, and that is equal to 0. So we do in fact get that the expected value here is equal to 0. So next, let's look at the variance of the score function. So we saw up above that the variance of the score function is equal to the expected value of U squared. So notice that that is going to be equal to the expected value of n over lambda minus the sum I equals 1 to n xi squared. Now I want to make this just a little bit easier on myself, so I'm not having to worry about the squares with the summation, so this is just going to be a notational thing. And notice here that I could make this the expected value of n over lambda minus n times x bar. So how did I do that? So let me write myself a little side note over here. I'm just going to kind of write it up here, kind of out of the way here. Notice that the summation I equals 1 to n xi, well, that's equal to n divided by n times the sum I equals 1 to n xi, because n divided by n is equal to 1. But if I have this part right here, this part right here is just really the sum I equals 1 to n xi divided by n, so that's just equal to n times x bar. Okay. So then I'm going to expand that. So now what I'm really interested in is the expected value of n over lambda squared minus 2 times n over lambda, the expected value of x bar plus n squared times the expected value of x bar squared. Okay, so we need to find some of these different pieces, so let's recall what we know about the exponential distribution with this parameterization. So recall, since x is distributed exponential lambda, we know that the expected value of x bar is equal to 1 over lambda. So in other words, it's equal to the mean. And remember that we also know the properties of the variance of x bar, and in general, x bar is always, the variance of x bar rather, is always going to be equal to sigma squared over n. So for this particular parameterization, the variance of this parameterization of the exponential distribution is 1 over lambda squared, and then we're going to divide that by n, and that is equal to 1 over lambda squared times n. And remember, you don't have to remember what these expected values and variances are for this particular parameterization. I typically, if I don't remember off the top of my head, I'll just go to Wikipedia, I'll double check, so if you want to do that, go ahead and double check there. So what this gives us now, substituting in some of these pieces, is that the variance of u, or we're just going to denote that as a capital V here, that's going to be equal to n over lambda squared. So this term right here, that doesn't change. And then we're going to have 2n times n over lambda times 1 over lambda plus n squared times the expected value of x squared. So we don't have the expected value of x squared yet, but we do have that trick that we've used in the past back in 675. And since the variance of x bar is equal to the expected value of x bar squared minus the expected value of x squared, we know, because we could rearrange this, that the expected value of x bar squared is equal to the expected value of x bar, that whole quantity squared, plus the variance of x bar. And we know that the expected value of x bar again is 1 over lambda, so that's going to be 1 over lambda squared, plus the variance of x bar, which is 1 over lambda squared times n. So now we're almost there. So now we have that V is equal to n over lambda squared minus 2n n over lambda, 1 over lambda. And I probably could have done some simplification before this point, but just so we see it all out, plus n squared times 1 over lambda squared plus n squared over lambda squared over n. And so now we can simplify this. Okay, looking here at the first term, we're going to have n squared over lambda squared. Looking at the second term, we are going to have minus 2 n squared over lambda squared. Looking at the next term, we're going to have, again, n squared over lambda squared, which is the same thing as n over lambda squared, plus, and then looking at this last term, notice that we are going to have a cancellation of the n's, so we're going to have n over lambda squared. And then notice that these three terms are going to cancel out, and so we're left with n over lambda squared. And so that is the variance of u. So next, let's see how we could use that and then relate it back to what we have seen in the past. Okay. So we have, remember that u is random, so we can talk about the asymptotic distribution of the score function. So here we have the theoretical result for the score may be obtained by applying the central limit theorem. And so one thing to notice here is that u can be written as the sum of independent random variables. And that's because we said earlier that u is equal to the sum I equals 1 to n ui. So that's how you're getting to where you can apply the, or part of why you can apply the central limit theorem. And so here is our results for our asymptotic distribution that we would get. And essentially what this is saying is that u is approximately normally distributed here with mean 0 and variance v1. And the mean is 0 here because we already showed the expected value of u is equal to 0. And so let's see what this means in terms of that exponential distribution. So applying what we found before, we know that u is approximately normally distributed with mean 0 and n divided by lambda squared. And you may say, well, how does that relate back to what we've seen before? Well, let's look at how it does. Let's actually write out what u is. So u in our exponential case was equal to n over lambda minus n x bar. So I'm just substituting in what u is here. And notice that u is a function of x bar. And a lot of times, we're interested in what's the asymptotic distribution of the mean for the exponential. And notice we can actually get that from this stage. Because the first thing that we can do is we can say, well, the mean of mu, or probably not mu, u is 0 here. But what if, so we've got the mean of u, which we know is equal to 0, but let's substitute this in for what u really is. Okay, and a lot of times, again, what we're interested in is the x bar piece. So let's see if we can find the expected value of x bar using this result. So notice this is going to be equal to n over lambda minus n times the expected value of x bar. And we knew that that was equal to 0. So let me actually, there we go, equal to 0. So then rearranging this, we have that negative n times the expected value of x bar is equal to negative n over lambda. So next we have that the expected value of x bar dividing both sides by minus n is equal to 1 over lambda, which is exactly what we knew was the expected value of x bar for the exponential distribution. So this gives us another way to find expected values of x bar. So this relates back and ties into those ideas that we've already seen. And you could do the exact same thing with the variance, and you would get the exact same answer. You would get 1 over n times lambda squared. And so this is how this is relating back into those ideas, that we have seen previously, but here we're writing it in terms of the score function. And so what I've written here, I've alluded to the idea that this could be done for multiple parameters, even though it was just written for theta. And so this last piece here is just talking about how this can easily be extended for multiple parameters. And so I'll leave you to read that piece on your own.